Good afternoon. We are Monkey C and we are here to present our machine learning model for predictive maintenance. Unplanned machine failures can cause serious disruptions, from costly downtime to safety risks. To address this, we use the Machine Predictive Maintenance Classification dataset from Kaggle. This includes 10,000 records of sensor data from CNC machines such as air and process temperature, rotational speed, torque, and tool wear. For our objectives, we aim to predict whether or not a machine is likely to fail, which would be a binary classification, and next is to identify its type if a failure is predicted. This would be a multi-class classification, where the model identifies the most likely cause from several possible failure types. The dataset enables the development of machine learning models to support proactive maintenance and reduce operational disruptions. So here's our dataset. So each row represents a single machine cycle capturing both sensor readings and failure outcomes. For the columns, we have the UDI, which is the unique identifier for each record, the product ID, which shows which product is being manufactured, the type, which refers to the product type labeled as L, M, or H, the air temperature and process temperature, which are measured in Kelvin, and gives the environmental and internal machine conditions. The rotational speed and torque, which helps understand how the machine was operating mechanically, the tool wear, which tracks down the usage of cutting tool, measured in minutes, and lastly, we have our target variables. The target column is a binary label indicating whether or not a machine failure occurred. So 1 meaning failure and 0 means no failure. The failure type gives us more detail specifying the cause of each failure, such as tool wear, overstrain, and others. So this would be the multi-class classification problem.
So for the data pre-processing and visualization part, the data used for this study was imported from a CSV file containing sensor data and operational settings for a predictive maintenance task. So our initial pre-processing involved inspecting the dataset structure, converting specific features like tool wear and rotational speed to a float64 data type, and dropping non-informative identifiers such as UDI and product ID. The feature set was composed primarily of numerical sensor data along with a categorical type column. To improve label quality, the dataset went cleaning to remove two classes of ambiguous entries, instances labeled as random failures and cases where target equals 1, indicating a failure, but the failure type was no failure. So these inconsistencies were removed to ensure that the labels aligned meaningfully with the prediction task, and this process led to a better percentage of total observations being dropped. And so next we have EDA, or exploratory data analysis, which was conducted to understand feature relationships and class imbalance. So a correlation heat map revealed interdependencies among features such as air and process temperatures. Uh, Pairwise scatter plots offered visual differentiation of the target classes, and the distribution of failure causes was then analyzed and visualized using a pie chart to show which showed the imbalance among the various failure types. So to address this class imbalance, a resampling technique called SMOTE was implemented to upsample underrepresented failure classes using random sampling with replacement, ensuring that each failure type was equally represented, and the resampled failure dataset was combined with the original non-failure data to form a balanced dataset for modeling. The categorical type column was encoded using label encoder to make it more suitable for learning algorithms, and the final clean dataset was split into input features X and binary target Y, representing machine failure occurrence. So for our model training and evaluation, the cleaned and resampled dataset was divided into training and testing subsets using an 80-20 train test split. So a random forest classifier was selected as the base model due to its robustness and interpretability. So a comprehensive grid search with cross-validation was conducted to identify the best hyperparameters, and the parameter grid included various options for the number of estimators, tree depth, splitting criteria, and class weighting strategies to handle class imbalance effectively. So the best performing model was identified using grid search CV, and this model was evaluated using several performance metrics. So these performance metrics are the F1 score, the ROC score, ROC AUC score, and the ROC curve. So for our F1 score, our model achieved an F1 score of 0.787, which indicates a strong balance between precision and recall. And the model also attained an ROC AUC score of 0.9897, demonstrating a good um, discriminative capability between failure and non-failure events. And so here we can also see that the ROC curve has an AUC of 0.99. So for the confusion matrix, here we have 19, 18, 5, 22, and 50. So this indicates that the models was able to capture non-failure and failure types pretty well, but there are still some cases of false positives and false negatives, which can indicate that the model still has more capacity to improve. And then we also have the cross-validation scores here, which further confirm the model stability and generalization with an average cross-validation score of 0.955 plus minus 0.081, suggesting very high performance across different data splits. And from our, we also ran feature importance evaluations, and it revealed that tool wear, torque, and rotational speed were the top three contributing variables to a failure prediction, along with domain knowledge in machinery diagnostics. So a learning curve analysis demonstrated the model's performance trend as more data was introduced, confirming that it was neither underfitting nor overfitting. And finally, model interpretability was enhanced using SHAP, or shapely additive explanations, and um, it reinforced that tool wear torque had the highest influence on predicted outcomes. So that's it for our model training and evaluation. So for the demonstration of our model, we have this front end interface that is hosted locally that has the model. So here we have the IPython Jupyter notebook for the model. So it lists all of the imports and then loads the predictive maintenance dataset. And then here we start our data pre-processing and cleaning. And we have our visualizations here for the feature correlation heat map and the scatter plot matrix for the important features. And then to fix the class imbalance, we have a representation of the classes before balancing, and then we also have the visualization of the classes after SMOTE, so class balancing, where all of the classes are now equal. Then after the pre-processing, we have hyperparameter tuning for random forest classifier, and then here we train as well, and then we have the model evaluation metrics. So this here is the F1 score, the ROC AUC, the precision recall F1 score, and accuracy. And here we also have the confusion matrix heat map, the ROC curve, and we also have the cross validation scores as well as the feature importance graph. Then we also have the learning curves and the SHAP graphs. So After it computes all of this, it will save the model, the best model, and dump it into a best RF model .joblib file. And so we use this joblib file to deploy the machine learning endpoint. And here on the browser, we have a front end interface for that allows the user to test different kinds of inputs and make the best RF model predict whether it will be a failure or not. So here, based on the base settings, it will say no failure predicted, and it also mentions the probability of failure. But as we change the different features, like the toolware, it still says no failure predicted, but the probability of failure increases. And so we can do this again. So now it's at 0.49, and now it starts to have machine failure predicted and probability of 0.52. And this also changes based on the machine type, which you can select, and it will predict the result. So all of this is done through this front end interface, which sends uh, the different parameters of the features and sends it to the trained model to make predictions.
Next is the benefits of the machine learning process. So the machine learning pipeline that we followed, problem formulation and data collection, to data pre-processing and visualization, model training and evaluation, and deployment, provides a structured and effective approach to building reliable models. For problem formulation and data collection, this helps us ensure that the task is clearly defined and that the solution is built on relevant and accurate data. So this minimizes the wasted effort and increases the chance of solving the right problem effectively. Next, for data pre-processing and visualization, this improves the quality and usability of the dataset, and it helps uncover the hidden patterns, correct imbalances, and prepare the data so that the models can learn effectively, leading to better performance. Lastly, we have the model training and evaluation, which involves selecting appropriate algorithms, fine-tuning parameters, and validating performance through metrics and explainability tools, resulting in models that are both accurate and interpretable for real-world applications.